All right. My name is Nikhil Roland. My partner is Bhuvan, and we are evaluating the efficiency of automated warehouses using a surrogate CNN model for our project. All right, so pictured in the slide, we have our warehouse environment that we're evaluating. Our goal is to optimize the efficiency of package deliveries in the environment. So these red dots representing multi-agents in the environment will pick up these green packages and deliver the most amount of them as possible to the gray squares in the least amount of time. All right, so for existing works, a circuit model like this already exists for single-agent game-based environments like Super Mario. And so in our approach, we extended this to a multi-agent warehouse environment. And because we're doing something new here, we have to train our own data. So again, we're generating our own data, and we generated 400 environments, so that is 400 warehouse layouts. Each warehouse layout takes 2 to 4 hours to converge, meaning calculate the number of packages delivered, depending on the GPU. And as seen in the density plot here, most layouts delivered anywhere from 30 to 40 packages in the specified amount of time, with some outliers as low as 15 and some as high as 45.
Yeah, I'll take over from here. Thank you, Nikhil. I'll talk a bit about the RL algorithm that we are using. We use an algorithm called MAPO. So we can, on the right, we see a chart that describes how the algorithm converges. We are training it for 20 million time steps, hence the time required 2 to 4 hours to train every single environment. And the reward to which the environment converges, to which the algorithm converges, we use this reward as a supervisory label to train our CNN model. So we have 3 sample warehouses here. Depending on the organization of shelves, the reward that they generate varies. So we'll talk about our main CNN architecture now. So this is our skeleton of our CNN model. It consists of 2 major branches. The red branch predicts something called as an occupancy grid. I'll come back later with example what an occupancy grid is. And the blue branch takes the input from the red branch and finally predicts our reward using an FNN and some CNN layers. So talking a bit more about the red section, we generate the occupancy grid. Like I said, an occupancy grid is nothing but the distribution of probabilities of the agent's locations over time. So it tells us which area of the warehouse the agents spend a lot of time. So we don't use max pooling layers to maintain dimensions, and we use ResNet layers because we want the model to remember how the original structure looked like. And that the blue section takes the input from the red section, and it stacks on top of our existing environment how an colored image stacks our RGB channels. So we see some examples of occupancy grids here. So in this environment, we see a clean passage, and the lighter colors means there is a higher probability, which means the agents are spending a lot of time in this passage delivering their shelves to the goal locations. In this chart, we see this isolated black section of the warehouse. So the agent can only go through this part, which is the reason most of the agents are avoiding this, which is a bad warehouse architecture in general and causes very poor reward. If you remember in the previous slide, this environment had a 16 reward. So coming to the results, because it's a regression model, we are using RMSE to evaluate our model. We tried different techniques. Using an occupancy grid gave the best possible outcome. And while training, we did the sampling as stratified sampling for the training data set. As we saw, there were outliers. Because of that, we did this. Yeah, this is the best possible thing we achieved. So to conclude, what we are trying to say is the occupancy grid is very important. It's something like a self-attention. It tells the model to on which region of the warehouse to focus on. And we use stratified sampling, which also trained the model well and made it robust to outliers. And finally, this model is productionized now. It can be used as a part of a larger RL or neural network model as a cost function, or it can be simply used to evaluate a given warehouse. Yeah, this is our project. Thank you for tuning in.